Okay, so yesterday we were talking about gravitational potential energy, okay? And we had decided that the equation for gravitational potential energy was this mess. Note the negative sign. That was a point of some discussion yesterday. Okay? As I was leaving, or as you guys were leaving, rather, Kurt pointed something out that actually was a really cool way of thinking about this. So some of you guys were a little bit frustrated by the negative sign, and what I had commented on was the fact that, well, it's still the same idea that, you know, if you move your two objects farther apart, then your gravitational potential energy increases just like you would think it would, right? Cool? All right. And so Kurt suggested looking at the graph, which actually makes some sense. So look, if you look at this equation, G is a universal constant. Presumably the masses of your two objects isn't going to change, right? So really, the only thing that's going to change is your radius, right? So really, this equation here is gravitational potential energy is negative some constant over r, right? So what does the graph of y equals negative k over x look like? Well, let's see what that graph looks like. Draw it over here. Y equals negative k over x. So 1 over x would look like this. Negative looks like this, right? Okay, and so Kurt's point was, well, look, our radius can increase all the way to... Sorry, thank you, I have my axis wrong. That's embarrassing. Pretend I didn't just do that. As my radius goes to infinity, my gravitational potential energy is still increasing to 0. So that was a great way to think about it, so thank you for sharing that. Does that make some sense, you guys? Okay, cool. So the book kind of gives this example where they've got these pairs of objects. So the idea is these two things have gravitational potential energy. These two things have gravitational potential energy. These two things have gravitational potential energy. So if you want to find the gravitational potential energy for the system, because energy is a scalar, you literally just add them up. So you find, you know, the potential energy for each pair, and then just add them up. Cool. Questions? All right, so that is the deal with gravitational potential energy. In a minute, I'm going to do an example where we will utilize gravitational potential energy to do some calculations. So before we do, we got to really quickly talk about escape velocity. All right, so I guess before we get there, a couple quick comments. So first of all, remember, we learned this when we did work in energy. Gravity is a conservative force, right? Okay, so that's still the case. The force of gravity is still a conservative force. So if I've got the planet Earth and I take some particle and I move it from point A to point G, no matter how I get it from point A to point G, the work done by gravity is going to be the same. Okay? The path that you follow to get there doesn't matter at all. That was one of our definitions of a conservative force, right? Does that ring a bell? All right. So to find the work done by gravity, what you'd do is you'd find the change in gravitational potential energy, right? You'd be gaining gravitational potential energy, right? And so the work done by gravity would be that number, but opposite, right? Because it would be moving this way, but gravity's pulling down. So the work done by gravity is negative, and the gain in gravitational potential energy is positive. All right, so you guys might remember we learned this equation, that the change in a potential energy is equal to the opposite of the work done by the conservative force associated with it. Does that ring a bell? So that's basically everything up to here. Cool. All right, this, I don't even know why I included this in here. This was sort of a frustrating statement. It basically says that you can calculate your force of gravity by integrating the gravitational potential energy equation, right? So, sorry, not integrating, differentiating. I take the derivative of it, but that's not very helpful because where the hell does this come from? So, all right. So, any problems with how to calculate gravitational potential energy, the fact that it's conservative, any of that work done by gravity? Are we good with that? All right. This is a useful little trick, you guys. This idea that the work done by gravity is the opposite of the change in gravitational potential energy. Okay, so there you go. Put that, what are you supposed to say? Tuck it away. I keep wanting to say put that in your pipe and smoke it. Put that in something. What is it? Put that in your. What do you got? Oh, put that in your wheelhouse? I don't think that's what I was looking for, but that works. Put that what?
Mentally file that away.
Mentally file that away. Thank you. It's not the expression I was looking for, but that says the same thing. Okay, now, escape velocity, or escape velocity, sorry. So escape velocity, do you guys know what escape velocity is? Somebody tell me what escape velocity is.
Velocity at which you can escape jet or the gravitational pull.
Okay, with one condition. Sort of. So does that mean that every time we send a satellite out into space, it has a velocity greater than escape velocity? That's the exit orbit. Matt, you got an idea? Got an idea? Well, if it's escaping, it's not in orbit anymore. That's part of the point. Right? We're trying to get away from the Earth. So how are... Sorry, I'm trying to decide how I can tell you this, so I'm just giving away the answer. So when we launch a rocket, like suppose we want to send a rocket to Pluto, right? Planetoid, whatever you want to call it, right? We're going to send a rocket there, okay? Or planet, or whatever. Those rockets have boosters on them, right? Like they have engines, in fact, that make it go, right? Okay? Those are not achieving escape velocity because they have a force that's continually propelling them forward. Escape velocity is like, here's a tennis ball. Throw this at a velocity so that it escapes the Earth. Do you understand the distinction? Okay? To be talking about escape velocity, you're talking about how fast it has to be moving at the Earth's surface and then have no more forces on it other than gravity to escape the Earth's gravity. Does that make sense? And so rockets don't qualify because they have an additional force that's helping them escape. You could escape at 1 mile an hour if you had a rocket that kept you always going at 1 mile an hour, right? What's that? I don't know what that is. The what? Oh, the Mars probe project. Gotcha. I just was considering the word Mars.
Did you hear about that?
No.
Oh, I had some of that.
Okay.
Somebody.
We'll show you. We'll show you some pictures.
Okay, great. Okay, yes.
Participation belongs to that's never a good idea.
He's about to ask a super important question. Say it louder so everybody can hear it. It's really important.
How do you escape gravity when there's always gravity acting on you from every single mass?
Right? Because look, you guys, the force of gravity never goes to zero, and your gravitational potential energy never quite hits zero, right? Okay? So, yeah, so it basically boils down to limits, okay? It basically boils down to limits, all right? So here's the idea. So our goal is we want it so that when we get to an infinite distance away from the Earth, what would our gravitational potential energy there be? Zero, right? So we want to still have some kinetic energy at that point. Does that make sense? All right. So what that means is this, that at the instant that you leave the Earth's surface, you have to have an energy such that your kinetic energy plus your gravitational potential energy is, I guess, not negative is the best way to say it. Okay? maybe the way that makes it more clear is to change the equal sign to a greater than or equal to. Okay, so the idea is right now I have a negative amount of gravitational potential energy according to our equation, right? Good. And as long as there are no other forces on me, my total energy is going to stay the same, right? Because the only force on me is gravity. Gravity is conservative force, right? So we need to give me enough kinetic energy so that my total energy, my kinetic energy plus my gravitational potential energy is equal to or greater than 0. Okay? Because what's going to happen is as you go up, you're going to lose gravitational potential energy. In other words, your gravitational potential energy is going to get closer and closer to 0, but we still want to have some kinetic energy left over. Does that make sense or no? Okay, if you wanted to make a picture of it, it would be this. So here's the Earth, here's me, right? So at this point, I've got a giant negative potential energy, right? So if I've got a giant positive kinetic energy, so that my total energy is 0, or bigger, then that means that when my object gets to a radius that's infinite, now my gravitational potential energy is 0, which means that my kinetic energy has to be greater than or equal to 0, right? In order to maintain our total energy being greater than or equal to 0. Does that make sense? So the idea, to answer your question, is now at that point you're now moving fast enough that gravity can't possibly slow you down enough to ever stop you. Does that make sense? In other words, you're getting farther away, and so as your radius gets bigger, your force of gravity gets smaller, and at this point, gravity is lost. Make sense? Yeah. Everybody good with that? All right, so look at this equation. So this is what's got to be happening at the surface of the planet. My kinetic energy plus my gravitational potential energy has got to be equal to 0 or bigger. Okay? So if you rearrange this equation, if you move this over and then solve for v, you get this. All right? And this is the equation for the escape velocity. Oops. This is the equation for the escape velocity of an object from the surface of that planet. Follow? On Earth, if you care, I'm doing this from memory, I think it's like 11.2 kilometers per second. 11,000 meters a second. So that means that if I wanted to take this apple and have it escape the Earth, I would have to throw it at 11,000 meters a second. That would depend on the time over which that velocity was changing. Right? Okay? But please understand, when we send rockets into outer space, they're not going that fast. Okay? Right? Because they have rockets. So this is the velocity that it has to have at the instant you release it, and from that point forward, there are no forces on it. It's just moving, it's got momentum, gravity's going to slow it down, but it'll never stop it. Yes?
I don't know if that's the way it takes a spin, but how?
Like 460 meters a second. Nowhere near that. Okay. In a minute, in a little bit, we're going to learn the velocity that something has to have to be in circular orbit, and it's like 7,000. So whatever this divided by the square root of 2 is. So even that's not fast enough to get it to escape. Okay. But it's a good starting spot, right? It's like, oh, well, already. Okay. Yes. Yes, this does neglect air resistance. Yeah. Yeah.
Do you know how much of a change the number would be?
I don't know. That's a good question. And one of these days, we're going to get around to going back to calculating drag force, which was something I talked about at the end of last semester. So maybe we can figure it out. So let's file that away.
How do you get
All right.
escape velocity?
I'm sorry? Okay, so that's the next thing I was going to say is, well, I just went through it, and it's super important you understand it, because I'll tell you, A, this equation, well, I don't think. This equation is not on the sheet that you are given
No.
during the test. All right, it is not on the thing. But you should be able to derive it. Look, it's a super simple derivation. All you're doing is, this equation is on there. The equation for gravitational potential energy is on there. And you all know the equation for for kinetic energy. So the equation is derived from just basically saying how much kinetic energy do I have to have so that when I add it to my negative potential energy, I get something bigger than zero, bigger than or equal to zero. Yes, that is one of the explanations, yes. Yeah. But yes, that's the easiest one. Make sense? Yeah, I don't like it either, I'll be honest with you, but it weirds me out. I'm right there with you if it helps. All right, so do you see what I'm saying, Patrick, or no? You need your total energy to be positive, so that when you get an infinite distance away, where your gravitational potential energy is zero, you've still got kinetic energy. That's what this is doing. Cool? Your total energy has to be positive, basically. Good? So that's a really good question, and I would strongly recommend that you maybe memorize this, but definitely understand where it comes from. It's this idea that your total energy as you leave the Earth's surface has got to be positive. That's it. Solid? All right, cool. So, and then just to note, like somebody talked about before, like the fact that where they launched the space shuttle from in Cape Canaveral and wherever Texas is, what's it called? Houston, there we go. We'll just go with Houston. There's a name for it, but yeah. Those are relatively close to the equator, right? Because then you're taking advantage of the Earth's rotation, right? And they launched them east to further, well, I guess launching them west, it would work against you. So that's why they launched east. All right, so are we good? All right, cool. All right, so here's a list of different escape speeds from different planets and moons and stuff. Look at it at your leisure. These two questions should be, well, here, take a second to read them. They should be pretty straightforward, hopefully. So it says you move a ball of mass m away from a sphere of mass capital M. Does the gravitational potential energy increase or decrease? If I move this ball of mass little m away from the ball of mass capital M, did I just increase or decrease the potential energy? Increased it. This is the exact same thing. I'm moving a little thing away from a big thing. I'm moving two things apart. Okay? It's getting less negative. I know the negatives. I'm right there. I agree with you 100%. All right, so does everybody understand? The answer to that is it increases because they're being moved farther apart, just like lifting something up a ladder. Cool? All right, part B, positive or negative work done by gravitational force between the ball and the sphere. So as I lift this, is gravity doing positive work or negative work? And there's two good ways to come up with an answer. Negative. That's one way to think about it. The force is down, the motion is up. And my GPE is increasing. And remember, that means that the work done by that force must be negative. Cool? Excellento. All right. Kepler's laws. So we're going to delve briefly into Kepler's laws, and then I'm going to backpedal and go back to energy for a minute and show you guys something. And you guys are going to be like, that is a giant pain in the neck. And then I'm going to say, haha, Kepler. And Kepler is going to show us a way cooler way of solving the same problem that is less of a pain in the neck. Good? All right. So, for years and years and years, I'm not going to go into the history, A, because I'm really bad at it. B, I wrote the word figure instead of figure. I just now realized that. I, for whatever reason, do you guys have like certain typos that you just make over and over? Yeah. I have two. That's one. I cannot type the word figure. I don't know why. And then ION is always OIN. All right. Anyway, so I'm not going to go into the history because I'm bad at it, and don't find it interesting. I'm sorry. But so for a long time, people were like, "Why do planets go the way they do?" Right? Like, how do bodies move in outer space? And this dude, Tycho Brahe, did you guys learn about Tycho Brahe?
Astronomer.
He did have a nose, but it was made of gold. He had a golden nose, and he wore stuff in his face with a leather thing. This is true. Say, what do you got, Nikki?
He got in a bar fight and he lost, and the guy got to cut his nose.
What was the bar fight over?
I don't know.
Who is a better mathematician?
Oh.
And so to resolve their dispute, they had a sword fight. Because clearly the person who's better at a sword fighting duel is a better mathematician.
We also learned in astronomy that he used to throw like these awesome parties, and you're not supposed to leave your own party. So he went a week without pooping, and he died.
Something like that, yes. He died of complications that were either urinary or fecal in matter. Yes.
Tycho Brahe lost the argument because he was presumably the worst mathematician, but now we use his laws instead of the other guy's theories.
I know, right? I don't know who that guy is.
Well, no, we don't use his formulas. We use his.
His
He was
data.
the one that used
Yeah. Kepler.
Yeah.
Kepler found
Oh, he could use like his assistant, right?
Yeah.
Yeah. So Tycho Brahe was, let me see if I can remember this. I should have written it down. He was like the royal astronomer for the king of some little island somewhere in Europe that I don't remember now, and I'm sorry. But yeah, so he just like this guy was like, here, go use my observatory and collect data. So he did that for years and years and years, but he never made anything of it until, some number of years later, this dude, Johannes Kepler, came along and he was like, haha, I have 3 laws. So I'm going to tell you the 3 laws. All right? Before I do, I got to tell you a little bit about ellipses. I'm guessing this is stuff you know.
Yeah.
All right? So I'm not going to go into a ton of detail on this, but if I remember right, the last time I taught math, the way that I defined E and F are different than the way they're defined in physics. All right? So in math class, when you guys, find the eccentricity of ellipse, in ellipse it's A over F, right? Does that vaguely ring a bell? Okay. So in math, I always thought of this as being A. Is that how you guys remembered it, or no?
No, it was
No, it is half. Okay, great, good. Then we're back and forth. Okay, so A is what's called the semi-major axis. And yes, it's the distance from the center of the circle to the outside at the across the farthest possible axis. Okay? And then F is called the focal length. And it's the distance from the center to your focal point. Oh, do you see? Then let's use C, honestly, because it doesn't matter. It's not an equation. So let's use C if that's what you guys are used to using.
No, you're right.
That's cool. It doesn't matter to me at all. All right. And then the eccentricity is the ratio between those two things. Cool. The one other thing that I find myself using occasionally is that if you pick any point on the ellipse's path and you draw a line from one focal point to that point and from that point to the other focal point and add those 2 lengths together, it gives you 2A. Oh. So I'm going to arbitrarily call this, let's call it R1 and R2. Anywhere on the ellipse, R1 plus R2 will always give you 2A. Useful fact. In fact, when I have taught like a regular physics class and we do astronomy labs, I have them put 2 thumbtacks in paper, and then you take a piece of string and and that's how you create an ellipse. Because the length of the string is fixed, right? Follow? All right, so I think that's what you need to know about ellipses. Cool? Cool. All right, so here is Kepler's first law. Kepler's laws, that's what these are. Kepler's laws. You realize I never labeled them. Oops. There's an extra parenthesis there, or an extra apostrophe there. You can figure out which one's the extra. So Kepler's laws. It's It's a contraction. It's actually Kepler. All right. Kepler. All right. This is the first of Kepler's three laws. It is called the law of orbits. All right. It basically says that the paths of celestial bodies, whether they're planets or moons or stars or whatever, they are elliptical. All right. And the object that they're orbiting is located at one of the two focal points. Cool? So, if this is the sun, here's the Earth's orbit. This is horribly exaggerated. Here's the Earth's orbit. There's another focal point over here. So these are the two focal points. The sun is one of them. Cool? Similarly, if this is the Earth, then this would be the moon. Good? All right. So, I guess I probably should have talked about this when I was talking about eccentricity. You should understand how the eccentricity affects something. Your eccentricity is always a number between 0 and 1. If the eccentricity is 0, the shape is a circle. You can remember that because a 0 looks like a circle. And the biggest eccentricity you can have is 1. If the eccentricity is 1, it's a line segment. You can remember that because the number 1 is a line segment. Good? All right. Does this make sense, you guys? Have you guys learned this in math, I assume? All right. Do I need to say anything more about that? I'm happy to if you guys want me to talk a little more about ellipses. Are we good? Had you not seen that before?
I've heard circle and line segments like that.
Okay. Yeah, I mean, all that happens, you guys, is look. Did you guys understand the string thing, or were you guys like, what the hell is he talking about? Yeah, so look, so here's my two focal points, right? I've got a fixed piece of string, right? If I put the two focal points together, and my piece of string is here, well, my two focal points are 1 point, so I'm just going to get a circle, right? And my eccentricity is going to be 0 over a, right? Because my two focal points are, the distance between them would be 0, right? Follow? And then, as I pull those two focal points, the two thumbtacks, farther and farther apart, eventually I'm going to stretch the string as far as I can. And then it's a line segment. Cool? I don't know. I always call them focal points. I think it's technically foci is the plural, or foci, and focus is the singular. I don't know. Funny. It's funny. I approve of that joke. What do you got?
Wait, so you said R1 plus R2 is 2A?
Yes.
So what if you choose a point that's all the way to one side?
That's fine. Because then, so you're going to have this length, which is most of 2A, plus this little bit here, is this little bit over here.
Okay.
Okay, really? Or,
Yeah, well, I mean,
right? Because this is A, 2A is all the way across.
I'm thinking of it like drawing a pencil with the string.
Yeah.
I'm not being correct.
Drawing a pencil.
Oh, I get it now.
Shut up.
You good? So,
I can draw a pencil. Yeah, I understand.
all right. I'll tell you what. Tomorrow I'll do it with masking tape and string on the board, and you guys will be like, oh, that makes sense now. All right. So anyway, let's move on. All right. So that's Kepler's first law. The orbits of planets are ellipses. Orbits of suns are ellipses. The object that's being orbited is at one of the two focal points, foci or foci, whatever you want to call it. Oh, good. Good. All right. Big rule number 2. So Kepler discovered, and this seems like a really weird thing to discover. Basically what this amounts to is the closer the planet is to the sun, or the closer the moon is to the planet, or whatever. I'm going to talk about planets and suns just to simplify things, all right? But so the closer the planet is to the sun, the faster it moves. Which should make a little bit of intuitive sense, right? There's more gravity when you're closer, so it feels like it should sort of be moving faster. There's also some conservation of energy there, right? If you're closer, you're going to have less gravitational potential energy, which means more kinetic energy. Good. So if that helps. All right. So that makes some intuitive sense. And Kepler took it a step further, and he realized that if you pick any amount of time, 1 day, 1 hour, whatever, if you pick a random amount of time, 1 day, the planet will, in any 1 day, will always sweep out the same area during that time. So, if this is the Earth orbiting the sun, if the Earth is here at noon today, and it's here at noon tomorrow, and you find this area that it sweeps out, so that sort of orangish area, that area will be the same for any 24-hour period you pick. So 6 months later, here it is at noon 1 day. All right, at noon the next day, it's going to be way over here, but this area is going to be the same as that area. Cool? Say that again. Do what on the TIA?
The integral of 4.
Oh, finding that area? You guys actually know how to do it, because it turns out, have you guys ever learned, it sounds like you guys didn't get a lot of cross products prior to this class, is that? Okay, so it turns out when you take a cross product, you're actually finding the area of a parallelogram. Here, I'll do it real quick. I don't want to get into a ton of detail with it, but suppose this is vector x, and this is vector y, and I do vector x cross vector y. That's the same as xy times sine theta, right? Well, look, here's x, here's y sine theta. Right? And then it's just length times width, right? Like if you take this little chunk here and move it over to here, you've got a rectangle that has an area of x length times y times theta, height. Cool? All right. So, great. So why am I talking about cross products? So it turns out that this will all be tied together at some point here. We'll do an example and you guys will be like, aha, now it makes sense. So it turns out that Kepler's second law, this idea that we sweep out equal areas in equal times, is the exact same thing as conservation of angular momentum. All right? The idea is there aren't sort of any external torques acting on your planet as it goes around the sun, so your angular momentum ought to stay conserved, right? So that means that if you find the initial angular momentum of the planet when it's here, it ought to equal the final angular momentum of the planet when it's over here. In other words, mass times Ri cross Vi, well, cross product, area, equals mass times Rf cross Vf. Put my little vector hats on there. Cool. Questions? Okay, yes. You could, so when you do that, because this is basically a point particle orbiting, right? So remember, I for a point particle is mr squared, right? L is I omega, so that's mr squared, that's I, times omega, but omega is just V over R, and you get mrv, which is what this is. Cool? Everybody good? All right, so while my 6th hour was taking a test, I was looking these notes over and I was like, ooh, we need a good example. So right at the end of 6th hour, I decided to do this example. So yesterday, our example, the hole through the earth worked out that I hadn't done before, so hopefully this one will go well. So I hope you guys are okay with this. All right, so, all right, well, I'm curious if you can do that. All right, so I'm going to take a brief tangent from Kepler's laws. And I'm going to tell you some stuff about Halley's Comet.
Oh, yes.
Right? Where did I write them? Right here. I scribbled them on this piece of paper here. All right, so here's some stuff about Halley's Comet. Anybody know anything about it? Okay, yeah, it only comes around every, what is it, 150 years or something?
76.
76 years? Okay. I don't know astronomy very well, clearly. All right, but yeah, so the reason it doesn't come around very often is because its ellipse, the ellipse of its orbit around the sun, has a very high eccentricity. All right, so there's a very brief period of time where it's very, very close to the sun, which happened when I was a kid. I remember being like 8 years old and everybody talking about it. And then it spends a lot of time very far away from the sun and therefore the Earth. Okay? So here's some stuff about Halley's Comet. Its orbit has an eccentricity of 0.967. That's almost a line segment, which is important. I know you're joking, but it's important. All right? Okay, now, it has a semi-major axis of 17.83 astronomical units.
This is from the Earth to the Sun average.
Very good. Yes, 1 AU is the distance from the Earth to the Sun. Very good. Anybody know how long it is offhand? We're going to have to convert this stupid thing to meters.
7,000 miles.
It is more than 7,000 miles. Because it's the distance from the Earth to the Sun.
7,000 miles from the sun.
So, I want to go with 1.99 times 10 to the 30th, but now that I think about it, I think that's the mass of the Sun.
Only by a factor of 10 to 20.
Did somebody Google it? You guys are not helping me.
Nope.
We'll call it 1.5 times 10 to the 11th. Cool. Oops. So 1 AU, what did I just say, 1.5 times 10 to the 11th meters? All right, so what's that give us? 1.5 E11 times 17.83 gives us 2.67 times 10 to the 12th meters. Okay, so good? Okay. So, it turns out, according to a random website that I found, that the maximum velocity, oh man, we're totally not going to have time to do all of this again. That's okay, we'll finish tomorrow. That's why I made the homework this Thursday. And this isn't even on the homework, so the maximum velocity that it achieves is 54 kilometers per second. So we'll convert that to meters per second. There we go. All right, so we ought to be able to find the smallest speed that it achieves. Okay? So we're going to do this two different ways. All right, the first way that we're going to do it is using conservation of energy. All right, so in order to use conservation of energy, we need to get a better picture for the orbit.
We have to know when it's farthest.
So we got to know, exactly, so we got to know when it's farthest and when it's closest. You guys understand that this maximum velocity is going to be achieved when it's closest to the sun, right? Okay, which I think is that perigee or apogee? I should have looked it up. It's one of them. I'm positive that it's one of them. All right, so anyway, okay, so let's draw this thing. So, all right, so here's the sun. Here's Halley's Comet's orbit. I'm going to make a horrible ellipse. Almost a line segment. All right, here's our other foci. All right, here's the sun. Here's foci number 2, or focus number 2. All right, so let's see. So here's what I know. I know that. So basically, I need to know two distances. I need to know this distance, and I need to know this distance, right? So the idea is, at this point, I know that my velocity is 54,000 meters per second, right? And the question is, what's the velocity over here, right? Make sense? So in order to do that, I need to know my R, which I will call over here, I'll call this R1, and we'll call this one R2. So I need to know the two radii. So, thoughts about how we can figure that out? I know both A and E.
Oh, is it my C?
Yeah, so we can find C, right? So let's see. So I'm excited to be doing this example. It's taking a little longer than I hoped it would. Okay, so let's see. So this means that C ought to be E times A, right? So that's 2 point, what was my C? Or what was, oh, E is, sorry. E is 0.967, is that what I said?
Yes. Yes.
And my A is 2.67 times 10 to the 12 meters. So that's going to be a number. I'm certain of it. Times 0.967. So that gives us 2.586 times 10 to the 12 meters. All right. So on my drawing here, that's this bit, C, right? Oh, yes. Thank you. Good save. Thank you. Yes. Okay. So thoughts? What's this distance? That's 2A, right? So 2C minus 2A will give me these two little bits, right? Oh, in fact, you know what? I'm overcomplicating this, aren't I? Let's just do this. Let's just go with A. Call this guy A. And then I can find this little bit here, right? Does that make sense? So R1 is A minus C, right? Everybody agree with that? Okay, so that gives us minus 2.67 times 10 to the 12. So that gives us 8.8 times 10 to the 10th meters. And so then R2, how can I find R2? Okay, so there's a couple of ways of doing it. You can do 2C plus R1. You can do 2A minus R1. Right? So whatever makes the most sense. I like 2C plus R1. That works. Whatever. So plus 2 times 2.675 times 10 to the 12 gives us 5.2617 times 10 to the 12 meters. All right. And I don't think we're going to have time to do anything from there. So I tell you what, here is your 10-second homework assignment. Oh shoot, did I jump the gun here? Oh, no, I did not at all. Okay, so find any potential energies that you can at either this point or that point, and then find any kinetic energies that you can. And then we'll see where we have to go from there tomorrow, all right? Cool? So, in other words, find the potential energy here, find the potential energy here, and find the kinetic energy here. Okay? And we'll pick up there tomorrow. Say that again? It is. Times 10 to the 10th. Do you see what I'm saying? It's like 1% of the other values, right? Follow? So yes, it's a big distance, but compared to 10 to the 12, not quite as big. Follow? Good question. I hope you guys are okay with this, me kind of making up this example here at the last minute. I think this will be instructive.